Last video we learned VT graph, so in this video we're going to work on acceleration and AT graph. First of all, the definition of acceleration is the rate velocity changes, or change in velocity over changing time. Take these two scenarios here for example. In the first scenario, the changing velocity over any consecutive seconds is 2 meters per second. So we can say the acceleration is 2 meters per second squared. And for the second scenario, the changing velocity over any consecutive second is negative 2 meters per second. So we can say the acceleration is negative 2 meters per second squared. The acceleration can be negative because it's a vector, and a vector has both direction and magnitude. You can understand it as positive acceleration is accelerating to the right, and negative acceleration is accelerating to the left. Now, the most common misconception here is when deciding whether an object is speeding up or slowing down when experiencing an acceleration. Let's consider 4 scenarios. I separate them into 2 groups. One is when the acceleration is positive 1 meter per second squared, and the other one is negative 1 meters per second squared. Let's consider this example here first. So the initial velocity is negative, so it's in this part over here. Let's say it's negative 2 meters per second at first, at 1 second. And we know the acceleration is positive, so the change in velocity is positive. The final velocity must be larger than the initial velocity. So after 1 second, the velocity will be negative 1 meter per second. Let's draw it on the VT graph. We connect the data point. We can see on the VT graph that the y data point is getting closer to the x-axis. So what we can conclude that is the object is slowing down. Now let's consider the scenario when the initial velocity is positive. Let's say originally it's moving 1 meter per second. And since the acceleration is 1 meter per second squared, we would expect that the velocity when t equals to 2 is 2 meters per second. This is pretty, you can understand it intuitively. So we can draw it on the VT graph. We can see the y data point is getting further from the x-axis, meaning that it's speeding up. Now let's consider when the acceleration is negative. At first we have the initial velocity is negative, so let's say 1 meter per second. And since the changing velocity or the acceleration is negative, we would expect that the final velocity minus the initial velocity would be negative as well. So at t equals to 2, the velocity is negative 2 meters per second. And if we plot it on the VT graph, we can see the data point is getting further from the x-axis, so it's speeding up. And for the last scenario, when v0 is positive, let's say originally it's moving at 2 meters per second. And since the changing velocity is negative and to the left, we can say at t equals to 2, the velocity is 1 meter per second. And we draw it on the VT graph. We can see the y data point is getting closer to the x-axis, so it's slowing down. So what can we conclude from this stimulation? We can see when the sign of the velocity and the acceleration match, the object would speed up. But when they don't match, then the object would slow down. It's same here too. When the acceleration is negative but the velocity is positive, we would see the object slowing down. And if they do match, we can see the object speeding up. So here we have our physics facts. If acceleration and velocity have same direction, then the object speeds up. On the other hand, if acceleration and velocity have opposite direction, then the object slows down. You might think, what if velocity is constant? Well, then there's no changing velocity and so it's no acceleration. You can see in this scenario, the velocity is always 2 meters per second. And what would we expect on the VT graph? So if we draw a VT graph, we would expect a horizontal line. So we know that from the previous video, the slope of the VT graph is the acceleration. So if we have zero slope, then that just means zero acceleration. Now, let's look at acceleration versus time graph. Since in AP Physics 1, you would expect most of the time the acceleration is constant until you reach simple harmonic motion, you would have a weird AT graph. But in kinematic, you would usually expect these horizontal line on the AT graph. So there's really just 3 scenarios that you can think of. The first one is when acceleration is positive. The second one is like this scenario when the velocity is constant, so zero acceleration. And the third scenario is when the acceleration is negative. So you might already know, like, if the acceleration, if any point, it's on the positive quadrant, that means the acceleration is positive. And if there's any point on the negative quadrant, then it would mean the acceleration is negative. And the final thing we need to know is area under the acceleration versus time graph. I would argue that this one is not as important as the area under the VT graph, but let's think about it. The area under the AT graph would be a times t, and we know acceleration is changing velocity over changing time. So let's plug it in. So the area will equal to changing v over changing t times t equals to changing v over t final minus t initial times t. We know that, see here, t initial would just be 0. So basically we can just ignore this part and just treat it as a time interval instead. So these two would cancel out, and we can see the area under the AT graph would just be changing velocity. Okay, that's all for this video. Next video, we will do more practice and connect all kinematic graphs before we can get into the kinematics equations. All right, see you next time.